what is quantum field theory? And why should you be taking it? The short answer is best given in terms of the modern perspective, which is that quantum field theory is a combination of the developments of fundamental physics over the past 100 years or so, maybe a bit longer. So what is it? So firstly, the Q part is quantum, right? And then the field part has to do with relativity and electrodynamics. In terms of, it's not specific to electrodynamics, especially you guys who know some particle physics, you know, but it's really how it began. And so, the short of it is that in modern language, QFT is a combination of our study of the symmetries of nature and also the application of quantum mechanics to many body physics. I'll call it variable body physics. So this is sort of the 30-second summary of what is the gist of quantum field theory. So let me warn you that, especially if you are a theorist, quantum field theory is about the deepest and most difficult thing you will ever learn in physics. Right? So relativity has this reputation, general relativity has this reputation, but it's completely false. Right? It's general relativity, once you know the basic framework, which is not easy, but it's once you know it, then that's it. But quantum field theory can keep on going on, and you're still not done. You can pick up any book on QFT, and you go on, and by the 300 pages, it's still doing some basic stuff because there's so much formalism, so much technicalities, so many conceptual issues, which you're combining so many things together that if you're a theorist, this is a side remark, but it's very important for theorists. If you want to be a good theorist, you want to make it as a full-fledged theoretical physicist, you need to learn your quantum field theory as well as possible, no matter what you're doing, right? And so, before I go there, let me just elaborate a little bit. So, in particular, the history of quantum field theory came about essentially from trying to combine our knowledge of special relativity and our knowledge of quantum mechanics. This happened about 100 years ago. Right? And the generalization of the development is why I say symmetries here. In particular, what kind of symmetries do we have? The one that was historically very important was Lorentz symmetry, which is what we learn as special relativity when we were undergraduate. But in this course, I would emphasize it as Lorentz invariance, or Poincare invariance. In fact, that's what I'm going to. Once the technical aspects of this class begin, I'll begin in fact with the study of Lorentz symmetry. What is Lorentz symmetry? And you'll see that a lot of field theory that you encounter is a consequence of this symmetry. And of course, why we know about it is because of electromagnetism, right? And this is what we're going to study. Relativity, and we're going to phrase what we learn about Maxwell's equations in terms of relativistic concepts, fully relativistic concepts. We'll see how it goes. But once you try to marry the symmetries, merge the symmetries, particularly the relativistic symmetries, to quantum mechanics, what you find is that the quantum mechanics you learn up to now, if this is your first time taking quantum field theory, all the quantum mechanics that you've learned up to now, you'll discover is not sufficient to account for this relativity symmetry, the Lorentz invariance that we will start talking about very soon. And so the way we teach QFT these days is to actually start from a field perspective, because it's easy to see the Lorentz and special relativistic properties, and then descend from that, and you will see how to properly combine the relativistic aspect, which is part of the field of the QFT, with the quantum. Right? But this is also where the variable body physics aspect comes in. Maybe I should add a few more examples. So symmetries, in particle physics, people also care about gauge symmetries. I won't talk about it so much for the moment, but this is important because it's actually also related to the microdynamics. The standard model of particle physics involves these special unitary groups. But let me just skip over this for a moment, but I just want to mention there are many other symmetries that show up in QFT, in the modern development of QFT, on top of what was originally discovered back 100 years ago. But as I said, when you try to combine quantum with fields, you discover very shortly that this in fact amounts to a formalism that will allow you to describe variable body physics. So what do I mean by that? That basically means that the number of particles is not conserved. And this is where the variable part of it comes in. Okay, so a simple example is when you turn on the lights of this room, you are basically creating photons. So in the modern language, we all know that light is made of particles called photons. But where does that come from? Why are you able to create these particles called photons? How do you describe this in a quantum mechanical way? And this is in fact what the core of quantum field theory is. You can even, in some examples, you can even ignore the relativistic part, where there are condensed matter systems where you don't need to care about relativity. But the many body, the variable body aspect of the quantum field theory is, in fact, often the crucial content of why people do QFT. So this also brings me to what are the range of applications, and I won't be able to finish talking about it, in fact. So there are, what's the physics behind it, and what kind of range of applications that we can describe. So in fact, I just mentioned this, a lot of condensed matter, where you might think that a lot of the development in quantum field theory came about through particle physics, electrodynamics, and so on. But these days, describing exotic materials, things that you can build in a lab, how electrons behave, how material behave in a bulk manner, this is what's called condensed matter physics. This whole subject is just as sophisticated, it uses just as sophisticated quantum field theory as what the particle physicists do. Right? So in fact, the development of quantum field theory has oftentimes, especially over the past 50, 70 years, ran in parallel between the condensed matter community and the particle physics community. Right? So don't think, oh, condensed matter is just, you're just talking about a piece of stuff, in the map, right? It's not like that at all. The fundamental framework behind condensed matter, the description of quantum many-body physics of your material, is nothing but the same quantum field theory that particle physicists use to describe the Higgs boson, hadronic processes, and the same underlying framework. So in fact, the example that is relevant for the past few years, what we call the Higgs mechanism in particle physics, in fact, is known as the Anderson mechanism in condensed matter, because it was actually Phil Anderson, Phil Anderson, who in the condensed matter community first proposed this idea of spontaneous symmetry breaking. And it was only later on that the particle physicists, Higgs, Kibble, there's a whole list of names that came along and implemented a relativistic version of that, which we now call the Higgs mechanism. So again, if you are a theorist, I recommend reading widely and teaching yourself as much quantum field theory as you can while you're a grad student. So that's condensed matter. Of course, cosmology these days. I'm starting from this ordering of topics is a little bit idiosyncratic, but cosmology these days, for example, is no longer just taking Einstein's equations and then you evolve it and you see you have the Big Bang and then you have nucleosynthesis and all that. It's gone way beyond that to the extent that when you start talking about the early universe, for example, and this is where people start talking about inflation, you discover that if we wind the clock back very, very to the very earliest epoch of our universe, that everything was much denser, things were much closer together, that you can no longer ignore the quantum aspects of the fields, the stuff that make up the universe. In particular, for inflation, the idea behind inflation is that it not only explains why different parts of the universe appear to be causally connected with each other, even though if you just, without inflation, you would not expect them to be. Not only does it explain that, if you turn on quantum mechanics during the early universe, and this is where the quantum field theory part comes in, we discover it also can potentially explain why structure exists, why we exist, in fact. So the idea, very briefly, is that there are quantum fluctuations in the very early universe, and that creates inhomogeneities in the structure of space in the early universe. And once there are places where it's a little denser and places where it's less dense, then matter will start to collapse. Places where it's slightly denser, more and more matter will start to accumulate there. And this is how, with the passage of time, you get galaxies forming, you get planets forming, and that's how we exist as on on this planet. If the universe was completely homogeneous and it was completely isotropic from the very beginning, then you would question, well, how do things even form? How can we form structure? So it's quite possible. I should emphasize, it's still this is still a speculative theory. We have more and more evidence for it, but it's still not considered established science, right? But we have mounting evidence that something like that is possible, and if it holds up, that would mean that quantum field theory's relevance, in fact, goes right down to our own existence. Why do we exist? Because of quantum field theory fluctuations in the very early universe. So these days, even when you're cosmologists, it's no longer just classical general relativity that you need to know, but you also need to know quite a bit of quantum field theory if you want to contribute to the forefront of research. And of course, particle physics itself, so my ordering of subjects is a little bit idiosyncratic. But this was obviously the beginning of it all. Like we from about maybe 75, 80 years ago, we discovering, actually I think the first discovery was Anderson, which I'll talk a little bit about but the development of quantum field theory went in parallel with our discovery of particle physics. And so a long time ago, 100, 200 years ago, we only knew about Maxwell's equations. And then it was discovered, the electron was discovered, which had a negative charge. And then the proton was discovered. All these came about together with our understanding of quantum mechanics as well. To understand atomic structure, we have to know what are atoms made of. So we discovered the proton, the neutron, the electrons. But that wasn't enough. As time went on, we discovered more and more species of particles. Good. Yeah, I'm just going to literally start the recording again. My camera can only record 30 minutes at a time for some reason. Okay, so what I was alluding to is the fact that the strong force, because it's so strong, does not allow free quarks and free gluons to be seen. So even though we know that the strong force is there, otherwise the nucleus will break up. The nucleus, as we know, is made of protons and neutrons, and the protons and neutrons themselves are made of quarks and gluons. So it wouldn't be there without the structure of the nucleus and the structure of the protons and neutrons would not be there if not for the strong force. But yet, we cannot see the expectations that we will not be able to see free quarks and gluons in nature, where nobody has seen one at least. And so this is called the problem of confinement. That the force is so strong, the quantum mechanical force is so strong that it's not possible to pull a quark out of a proton. Or pull a gluon out of a neutron. It's just not possible. And we know, we have arguments for it, we have theoretical arguments for it, and we certainly have very strong experimental evidence in favor of it. And nobody has seen it before. This is why quantum field theory is still such a vibrant subject. If we can prove rigorously confinement, that as you create our theory, so this will be very brief about the development of quantum field theory. So I basically told you what quantum field theory is for, right? And what the conceptual, this is a very rough, obviously a very rough overview of the conceptual underpinnings of quantum field theory, as well as what the applications are for. Right? So in fact, our proof also reminded me There's much more than that. Right? So for example, particle creation happens in cosmology, happens in particle physics, also the thing called the Stringer effect. So spontaneous particle production is something that I think many people get very fascinated by this, because it's a purely quantum field theory effect, right? So this signal that particle number is not conserved. There's a Stringer effect. There's a Hawking effect in black hole physics, and so on. Those are examples of quantum production of light. I think it's quantum at the fundamental level, but this highlights in the quantum character at the very fundamental level. But so that's the overview. But I do want to briefly also mention how do we get here? So how do we get to quantum field theory itself? And give you a flavor of kind of the quasi history behind it. Before I start talking about relativity itself. So let's do that. So let me just say the words first. Of course the original development of quantum field theory came because of quantum mechanics, right? So we knew from atomic spectra and black body radiation and so on that the rules of physics when you're dealing with microscopic phenomena was quite different from what we're used to in the macroscopic world. And so it took a while, but people like Heisenberg, Schrödinger, de Broglie, and all of these big names, Bohr, Sommerfeld, they gave us what we call quantum mechanics. So in fact, this is where we should begin. Right? So we should remind ourselves that quantum mechanics was interested in atomic spectra. And so back then, we only knew about photons, electrons, and then subsequently we knew about protons and neutrons and so on. But let me just focus on these two as an example, as introduction, quasi-introduction to the history of quantum field theory. So photons began as fields because we knew them as the light that comes from the sun, the light that comes from the light bulb, and so on. But later on, we discovered that they were particles. How do we do that? It was thanks to Albert Einstein, who tried to explain the photoelectric effect. So I won't go into that history, but hopefully you heard that in quantum mechanics class. Right? And so he discovered that if you postulate that photons are particles, not waves, you can explain the photoelectric effect. And then later on, people realized that that same postulate, the particle nature of photons, can also explain the black body radiation. Right? So I won't go too much into that, but the chronology is important because later on, we discovered electrons, and of course, we first discovered them as particles with charge minus E. So negative charge is a convention, but we discovered that they have a charge of minus E. And it came in discrete packets. Right? That you won't find an electron with minus 1/2 or minus pi of E. There's no such thing. And in fact, in nature, we do know that it at most comes in 1/3 multiples of E. where the quarks have 2 and 1 charges, but protons, electrons, nothing has anything other than a multiple of E. Or if you're a quark, you have nothing but 1/3, 2/3, and so on. So it comes in discrete packets, and that's how we discovered that electrons were particles. But later on, de Broglie told us that no, maybe since photons are also waves, how about electrons can also be waves as well? And this is in fact the beginning of quantum mechanics. And then we all know that Schrödinger was the one who first got the right equation. And usually we call it the Schrödinger wave mechanics, where it's just the famous Schrödinger equation, and psi is the Schrödinger wave, so to speak, the wave function. But if you actually open up the first chapter of Weinberg, so actually I should recommend, so history of QFT is not something you find very much in Pascal and Schrödinger, maybe a little bit, but we should look at chapter 1 of Steven Weinberg's QFT book. So Weinberg wrote many books. So this is the Quantum Theory of Fields book, and he has written 3 volumes. Look at the volume 1. So volume 1 and 2 are basically the meat of quantum field theory. The third volume is about supersymmetry, which is becoming less and less important, I think, in particle physics. But if you want to learn your quantum field theory very well, that's my recommendation. Go through these 2 volumes. Although I would tell you it's very tough. Right? So you want to do it together with reading other books. But basically, it's like the Bible of QFT. Anyway, so back to Schrödinger wave mechanics. So usually that's where we stop, right? In quantum mechanics, we spend 2 semesters learning about this equation, how to solve it, and so on. But if you read Weinberg, he will tell you, in fact, both de Broglie and Schrödinger were actually concerned about relativity. Because remember that all this happened after 1905, after Einstein came up with relativity. So it was on their mind, and they were trying to create a theory, invent a theory that was consistent with relativity principles. But obviously they didn't quite succeed, right? So in fact, maybe I shouldn't say that. In fact, what I read from Weinberg is that Schrödinger actually discovered something that we now call the Klein-Gordon equation. Okay, so I should draw a line here, which is the Klein-Gordon equation does not describe electrons. But there's a history, which is that Schrödinger tried to get a relativistic equation for waves. And he stumbled upon now what we call the Klein-Gordon equation. I'm going to write down the equation, but you don't have to worry if you don't know what it means for now. But eventually you will. Okay? So this is the Klein-Gordon equation. It's really just a wave equation for scalar spin-zero particles. I'm using modern language now. Just a spin zero and massive particle. Okay? And they came up with it, again, because they wanted a wave equation that was relativistic. Schrödinger apparently came up with it, but he realized he had problems interpreting what this thing was. In particular, it didn't look like a wave function. It didn't have probabilistic interpretations that his wave function does. Right? So this gives you, as you know, this gives you probability. But psi, phi here does not. So he had trouble with that, and he kind of gave up because of that problem. And so, and in fact, it took a while. This was a problem. Right? Schrödinger came up with this equation, but we all know, if you're taking quantum mechanics, that what we usually end up doing is taking a non-relativistic limit. So the question is how to extend the Schrödinger's equation to relativistic situations. And so Klein-Gordon tried, and let me just cut to the chase. So it turns out that at least for electrons, right, which remember we first discovered them as particles, only later on we tried to come up with some kind of wave function for them, and then we had to generalize it so that Schrödinger's equation becomes consistent with relativity. So how do we do that? It actually took the genius of Paul Dirac to write down his equation. Right? And again, I'll write down the equation, and you don't have to worry about what it means for now. But this side here is not quite the same side as this guy here. So if you learn in quantum mechanics, psi is just a complex function of space and time. Sometimes you stick in by hand a spit, but this guy turns out not to be just a function of space-time. This is actually a four-component object. And this whole structure, we will spend some time trying to understand it. So I just want to outline what happened as a kind of a pseudo history, but I will return and build these things up bit by bit. So Dirac came along and told us that no, the way to generalize it is not through Klein-Gordon. It's actually to promote psi to a four-component object, and these are matrices actually. These are 4x4 matrices. And the reason why they're special is because they allow you to get relativistic properties. So I should say, this in fact is an example of spin half massive particles. So Klein-Gordon is important, just not in the way they envision, but I'm using modern jargon to tell you that it is important because it actually describes spin zero massive particles. For the Dirac equation, it describes spin half. And maybe I'll just use this opportunity to say that in the modern language, photons, right, which obey Maxwell's equations, they are spin 1 massless particles. It's important to distinguish between massive and massless particles for spin 1 for a few reasons. One of them is that if you have a massive particle, we will discover that it will give you a short-range force. So the force that you experience from electromagnetism will no longer be able to propagate long distances. You won't be able to see the light coming down and then illuminating the room so readily. You won't have long-range Coulomb interactions anymore. And atomic physics would be very different if the photon had a large mass, for example. That's one reason. So mass Zero mass gives you a long range force. Massive photons will give you a much shorter range. But there's also a more fundamental reason related to the study of symmetries. Okay, so you will discover that when you have zero mass and you have spin 1, the study of the Lorentz, the special relativistic properties of spin 1 zero mass is very different from spin 1 but non-zero mass. Okay, so what I'm really talking about is the group theoretic properties, but for now I just want to use as simple words as possible. When you study the relativity, again, of spin 1 zero mass is not the same as spin 1 massive particle. So can you guys see this? It's not the same. And there is actually a, how to speak, maybe I'll say it here. So there is a similar situation for gravitation. So gravity or weak gravity. This is an aside. This obviously didn't come from the development of quantum field theory at the beginning, but now with hindsight you can say the following, which is that weak gravity corresponds to gravitons obeying Einstein's equations. And these correspond to spin 2 with massless particles. So gravitons are massless. Again, if gravitons were massive, they had a mass, then I'm sorry to tell you, you wouldn't be stuck to the Earth. The Earth would not be going around the Sun because the range of force is determined by the mass of the particle. So if the graviton has a big mass, for example, then that would tell you that the force between the Sun and the Earth could potentially be much weaker because it's becomes a short range force. Of course, it ultimately ends up being a constraint. Right? The mass needs to be small enough so that it's consistent with what we are observing. But from all the observations that we can gather, gravity is a long-range force. It's basically an infinite range force. And that points to a massless particle, or a massless graviton. Now, again, just like the spin 1 counterpart, this is not the same. You guys can see, but let me say it worse. It's not the same as spin 2 with a massive particle. Meaning, if you study the relativistic properties of particles of spin 2 with non-zero mass, and you try to crank the mass down to zero, you will find there's an abrupt change in the character of these particles. There will be an abrupt change in the group theoretic properties when you are working with either spin 1 or spin 0. There's this discontinuity that occurs. That doesn't, I should say, it doesn't happen for spin half, nor it happens for spin 0. It doesn't happen. But these are all relevant because all of these things occur in nature. Okay? So we know that there's now a Higgs boson. Although the full theory for the Higgs boson will have to extend this to include the interaction between itself and also with all the fermions of the standard model. Right? So, but let me just say that the example of spin 0 massive particles exists in nature. Higgs. Spin 1 massless, of course photons is an example, but gluons are technically also an example. But I just told you that the quantum nature of the force is such that because of that quantum, because the quantum effects are so strong, the strong force is such that even though gluons are massless, you cannot experience them at large distances. You If it's just too strong, you can't disentangle it from the nuclear matter. You can't take it out of the proton or neutron. Any questions for me? Yeah.
So if we think about gravity as
Yeah.
the deformation of space-time,
Yeah.
and we talk about gravity as
Yeah.
particle.
That's right, yeah. That's why I want to mention weak gravity, right? So it gets a little bit different if you're near a black hole or if you're near near the beginning of the universe in the Big Bang, near the Big Bang, then the curvature is very strong. Then what I'm describing here doesn't quite apply anymore. But so what I'm saying is really most applicable in weak gravity. For example, right here near the Earth, we are basically exchanging spin-2 gravitons with the Earth. That's why we're stuck to it. The Sun and the Earth are also exchanging spin-2 massless gravitons. And that's why they're stuck to each other. Yeah. Like I said, if you outline a mass, then if the mass were actually much larger, then the force will become much weaker. And then I'm sorry to say we'll be out of the solar system and we'll probably freeze to death. So let's hope that doesn't happen. Right? But does that answer your question? So that's the key point. That you're in weak gravity, and then there's now kind of a dual description. You can think of gravity as the curvature of space-time, yes, but you can also think of it as an exchange of massless spin-2 particles. Yeah. Actually, this is a good point in physics. When you do physics, when you learn physics, and someone tries to sell you a single perspective and tell you that's the only way to think about physics, you should ignore him or her. Okay? That's extremely important. In physics, there's usually no one way to think about things. Right? So this is an excellent example. The particle physicists are very adamant. Okay, it's a spin-2 particle, right? But what happens when you go to cosmology? Or what happens when you go to black holes, right? And then the general relativists will be very adamant. Oh no, gravity is not even a force. It's just curvature of space-time, and so on. Come on, pretty easy, man. Just it only enriches your understanding if you are able to assimilate more than one perspective to what's really going on in nature. Right? So that's actually an important point to me. Right? So thanks for the question. Good. Any more questions for me? What?
Discuss being zero, massive particles, Higgs particles.
Yes, that's an example of a spin-0 particle in nature. That's exactly what I'm trying to say, right? So photons give you this spin-1 mass equal to 0. Gravity gives you spin-2 mass equal to 0. So I should say, of course, we have not detected gravitons, right? So take that. This part should be taken with some skepticism, but quantum field theory actually itself tells us that it's very likely that even if the complete theory of gravity is a different one from Einstein's equations, at low energies, I think it's becoming more and more widely accepted that at low energies, it has to reduce to this anyway. It has to reduce to a massless spin-2 particle at low energies. When you're talking about quantum gravity in the long distances, not when you ask what happens at a very, very short distance. That we don't know. But at long distances, it's okay. It is actually okay to quantize gravity, and you should get this result. Yeah. Guys, do you want to ask me questions, or do you have any questions for me? Yeah. Don't be afraid to ask, but I just don't want to be distracted by other conversations as well.
I wonder how to define the spin of those particles.
Good. So I will get to this, right? But this is good. So I assume you guys have all taken quantum mechanics, right? Who hasn't taken quantum mechanics here? You're not taking quantum mechanics? Oh, good. Yeah. Quantum mechanics, right? Quantum mechanics? No. Who hasn't taken quantum mechanics? Okay. You guys have all not taken quantum mechanics. Okay, that's why you don't want to spin. Okay. So in quantum mechanics, so maybe I'll read this to a bit later, okay? But yeah, so that's of course a very important question. But what you should have done is if you're taking quantum mechanics and you have spin, you would have seen spin in the context of quantum mechanics. And then, let me just tell you in words what happens. Then you will discover that just as we are about to start studying relativity, we're going to start studying, in quantum mechanics, you start studying rotations. And the reason is because rotation is a symmetry of the fundamental laws of nature. And because of that, you can classify the properties of particles based on how they transform internally when you try to rotate them. So it seems like a very basic idea, but if you try to combine these two things, quantum mechanics and the study of rotations, you will discover that you can classify particles based on essentially how they rotate under in 3 dimensions. And spin is actually, it will turn out to be an eigenvalue of, so usually you label it by L and M, and this, there are 2 operators, right? So this is called the total angular momentum. And this will turn out to be L times L plus 1. And then you can pick a z-axis, which usually I'll call 3. So this is the jz, but I prefer to call it j3. And this will give you m times L. So this is the azimuthal quantum number, and this is the total angular momentum. It turns out that L is in fact what we call spin. And why we call it spin as opposed to just angular momentum is because in the case of Klein-Gordon particles and photons and gravitons, they are integers. So it can be 0, 1, 2, and so on. But once you come to fermions, you will discover that it can also take one half integer. So there's 1/2, 3/2, and so on. Okay. And so by spin, we'll get to this why this can be the case. But spin essentially is a property of how these particles, again, the quantum aspect of these particles, what happens when you try to rotate them in 3-dimensional space. And this is kind of an invariant property of it that characterizes what they are. Yeah. So keep that in mind, and then by the time we get to it in a few weeks, I think, if you still don't understand it, we can talk more. Okay? Any other questions?
So you just mentioned that the mass implies how long the force range.
Right.
So is that the reason why Higgs particle has been detected?
Not quite. The Higgs is hard to detect because it's very, it's heavy, but the reason why it's hard to detect because it's heavy is not because of the range of the force. It's just because you need a lot of energy to produce it. So you need to collide enough, you need to collide particles with enough center of mass energy to produce the Higgs. The Higgs is about 126 G. Okay, good. So, more questions for me, guys? Yes. Yes.
How can we know that the particles are rotating in the 3-dimensional space?
Yeah.
That it's
so what you're saying, let me paraphrase what you're saying, and then you tell me whether that's what you're asking. You're asking is, I cannot grab an electron and actually literally rotate it, right? It's an elementary particle. I cannot grab a neutrino and try to rotate it. I can't. It's an elementary particle. But what we can do is that we can work out the consequences of its spin interacting with, for example, magnetic fields or other particles. You will find, and this is actually why QFT is such an elaborate structure, you will find that different particles with different spins will allow for different types of interactions. And it is these interactions that we can detect. So for example, the electron spin, if you're taking a quantum mechanics course, I'm going to try to avoid writing that because I'm not recording. So for example, for an electron, how do we know electron spin? What happened was that we look at atomic structure, atomic spectra, and you find that there are situations where it's called multiplicity, but it just means that you get too many electronic levels than you would have expected. So I think this is due to Gold, Smith, and Gold, Smith. And this money moving back, down. So what they found was that to explain why the spectra had too many lines, it would work if you try to allow the electron to have an extra degree of freedom, which they postulated was due to its internal angular momentum, the spin. And then there's something called the Yi-Zen effect, which in fact is related to the interaction between magnetic fields and the spin of the electron. Have you seen this in quantum? You're not thinking about it. So this is an example, a simple example where there is an interaction between the spin of the particle and an external agent. In this case, the external agent is a magnetic field. And it produces consequences for the atomic spectra that you see, that you can then measure. And then from these two things together, you can actually not only deduce that the electron has spin, it has spin half. That's how we determine this. Yeah. In particle physics experiments, I believe one of the things that people do is when you collide particles and you produce new ones, right? And you look at what is produced. One way that people use to distinguish the spin of particles is actually the angular distribution of the outgoing particles. So different spin will produce different angular distribution. Meaning if you collide protons together and you produce Higgs, or you collide protons together and you produce neutrinos, the distribution of the outgoing particles that you produce has a different function and the angles, outgoing angles, depending on what the spin is. Right? So that is a crude way to need other observations as well. But there are ways. The point is that you use the type of interactions specific to the spin, work out the consequences. Right? In this case, the Yi-Zen effect is an impact on the spectral lines that you see. In particle physics experiment, the angular distribution is different, and so on. There are other ways to put it. But it's a good question. How do you measure the spin of a particle? It's not a trivial matter. But so far, all that we have seen is consistent with the quantum field theory description that comes from applying relativity concepts to quantizing fields. That's what we can say. Good. Very good. Okay, so where are we? Yeah, so Dirac equation, and then photons, gravitons, and so Dirac was the guy who started it all because from the Dirac equation, maybe I'll go a little faster because I want to yeah. Do you guys have any questions for me? Yeah. It's a little distracting from here because you guys are talking to yourselves and I keep thinking that you have a question for me. But so if you want to say something, by all means, just raise it with us and then we can discuss it. Okay? Okay, so let me be a little bit quicker because we are almost out of time. So it's actually with Dirac's equation that we realize something called anti-particle. So Dirac's equation allowed for both positive and negative energy solutions. And it turned out that, it took a while, but it turned out that the negative energy solutions were not a problem, but they actually corresponded to positrons, which are the antiparticles of the electron. So it turned out that actually it was discovered soon after by this guy called Anderson. I won't go into the details, but basically she brought this apparatus up a mountain, and we get these cosmic rays coming from the upper atmosphere. And he found that she could, by turning on a magnetic field, he found a particle that went in a curved track in his bubble chamber. So curved track in a magnetic field means that the particle is charged. And from the curvature, we can determine the charge to mass ratio. And it turns out basically it's like an electron, except that it would be curved in the opposite direction from the electron. So that's how he knew that he discovered the positive charge counterpart of the electron. This is important conceptually because it turns out that relativistic QFT predicts every particle has an antiparticle. Sometimes your own antiparticle, for example, photons are their own antiparticle. But for the electron, you will have the same mass positron, but if you are negatively charged, then the antiparticle with the positron will be positively charged. And this happens to a lot of the particles that you produce in colliders these days. If you can produce a charged particle, that it will be negatively charged counterpart, and so on. And furthermore, Dirac's equation, upon quantization, in fact, tells us something about the Pauli exclusion principle. It gives us a more firm basis of the Pauli exclusion principle, and it gives you and more generally it's called spin statistics. It gives you a relationship between the spin of the particle and how many particles of that type can occupy the same quantum state. So the answer for fermions, spin half particles is 1. At most 1, 0 or 1. But for bosons, which are integer spin particles, you'll find that you can have arbitrarily many particles of integer spin occupying the same quantum state. Right? So this is something that you learned probably in a quantum mechanics class, but there you were just told this is what it is. And in fact, that's what happened. Pauli just postulated this principle just so that he can explain, atomic structure. But he didn't know where it came from. But with the Dirac equation and this quantization, that we finally managed to have a better understanding of why it is the way it is. So by the time we do that, we'll see more of that. But I just want to give you some history. Okay, so I should finish up. So what happened was then, once Dirac came up with his theory, we realized that we had to find a quantum theory of the full system of the electron together with the photons. And this is really the true genesis of quantum field theory itself. Right? So I think it was Heisenberg and Pauli, and then Jordan, Heisenberg, Born, Jordan, a whole bunch of people that started this developing and then later on it was Heisenberg and Pauli. So let me just say, basically what you will see in a few weeks' time is that when you talk about at least free particles or weakly interacting particles, you can view the fields themselves that describe the electrons and protons as a sum over their Fourier modes. And each Fourier mode you will discover is like a particle in quantum mechanics. So instead of having just a particle, what you do is you first decompose your fields into modes, and each mode can then be associated with its own degree of freedom that you then apply quantum mechanical rules. Right? So let me just say this: Fourier modes of fields. In particular, what you discover is that each Fourier mode behaves like a simple harmonic oscillator. So the rules of quantum field theory, of quantum mechanics applied to fields, tell me that essentially particles, the heuristic view of particles is that basically they correspond to excitations, small vibrations of these fields on top of the vacuum. And what you're detecting when you build particle colliders is that what you're actually doing is that there's a field that permeates all of space-time, and by exciting it, you're creating a particle from the vacuum. And that's what you see when you see a track going through your bubble chamber, or a track going through your LEC, and so on. Okay, and then finally, let me just say that things were not so rosy actually. After this, people started calculating more elaborate processes, and they discovered that they couldn't handle the math very well. They ended up with a lot of infinities in their answers. So these infinities probably we won't encounter many of them in this course. Usually that's why you take the second semester of QFT, third semester even. But the punchline is that there are two types of infinities in quantum field theory. One is associated with massless particles, and because we can produce an infinite number of particles that are arbitrarily low energy. It doesn't cost anything because this massless. It doesn't cost anything to produce them. So you can produce them copiously. And because of that, there's what's called an infrared divergence that we can encounter. But we know how to deal with that because we understand how these particles behave. What's the more difficult problem that physicists struggle with in the 1900s, early part, all the way up to World War II, was the degree divergence, what's called the ultraviolet divergence, that come from the smallest length scales. And what you find is that most calculations beyond the simplest will give you infinities. And people struggle to figure out how to deal with that until people like Schwinger and Dyson, so just QED, quantum electrodynamics, there are always named Schwinger, Dyson, Feynman, blah blah. There's some other names, but these are the main players. They have kind of got the formalism to where we are today, at least as far as what we do in calculations. There are later developments that I don't want to go into right now that further explain what we're doing when we do these calculations. But they really lay the foundations. So let me just finish by saying, in fact, this is an example where the conservative approach to physics won the day. So at that time, when physicists faced all the infinities, it was the older, more senior people who advocated that maybe we should abandon quantum field theory. Maybe something is fundamentally wrong with whatever we're doing. But it was the younger people, these guys that are trying to be younger folks, they decided to take the conservative approach, which is to pick what you have and try to push whatever you have to its limits and see, does it work or does it not work? Is there a way to just still work with what you have? And in fact, for quantum field theory, the answer is yes. I'm not saying it's always true, but for quantum field theory, it turns out to be true. And we are still using these methods to calculate all these processes that we see in particle physics. Okay, any other questions for me?
How to read, there are two solutions. One is positive energy, one is negative energy from the equation.
Yeah, I'll come to that. Yeah, it's a bit technical, but you'll see that there are four components. It's a complex equation, and you find that there are two solutions. One corresponding to positive energy, one to negative energy, and there's also different spins and so on. But it will take a while to get there. Yeah. I just managed to be Any other questions?
I want to
Yes.
ask about Fourier modes. So you mean each Fourier mode implies how many particles we have?
Yeah, so it will turn out that Fourier modes allow you to create and destroy particles. That's the better way to say it. So if you've got the simple harmonic oscillator problem in quantum mechanics, that is a very important problem to be familiar with. Because what you discover is that you can write, just like in quantum mechanics, you can write the simple harmonic oscillator problem in terms of the Hamiltonian looks like this, where 1/2 A dagger A plus 1/2 of plus 1. Right, you remember, this is the simple harmonic oscillator Hamiltonian. And the reason why it's important to put it in this form is because these guys obey a particular computation relation. Okay? And with that computation relation, we can show that A dagger applied to the zero particle state will keep creating more and more particles. The more you apply A dagger squared, A dagger cubed will create 2 particles, 3 particles, or in the harmonic oscillator case, you excite it to the second excited state, or third excited state, and so on. In the quantum field theory situation, you will discover that when you apply the analogous A dagger on the 0 particle state, you are basically creating more and more particles of that Fourier. And you apply A on your state, you are decreasing the number of particles. So when you apply the rules of quantum mechanics to Fourier modes, you discover those modes behave essentially like a harmonic oscillator. But the interpretation is a little different in the sense that now you're creating and destroying particles, but not exciting them in different levels. Right? In the harmonic oscillator case, you're going from the 0th level to the 1st, 2nd, and so on. But the particle number is the same. You're talking about a single particle with the harmonic potential. But in the QFT case, you're actually creating more and more particles. So there's a bit subtle, but anyway, like I said, I meant this to be an introduction, where just to give you a flavor of the range of what QFT is about and how it came to be what it is. And but this part we will certainly do it in some detail. We will quantize a scalar field and see exactly how this harmonic oscillator structure is. Any other questions? Okay. So please respond to the Doodle poll, and I will see you guys on Friday.